Welcome to day 11, 3.7, optimization. This is the first part of optimization. So our goal is going to be minimizing and maximizing different aspects. Okay, so let's take a look at this first example. 2 points are on that curve given y equals x cubed over 1 plus x to the fourth. But they have opposite x values, so x and the opposite of x. So we want to find the points making the slope of the line joining them the greatest. So if we show the setup here, I need to choose some point x and then the opposite of x. So to find those y values, all I did was plug x into our equation, x cubed over 1 plus x to the fourth, and we're just left there. When we plug the opposite of x in, well, negative x cubed stays negative, and the denominator stays 1 plus x to the fourth. Now, the key here is it wants us to making the slope the greatest is this key phrase right here, right? Making the slope the greatest, that's telling us to maximize slope. Okay? So when I see the phrase maximize or minimize something, we have to think calculus. We have to think, okay, what do we use to determine if something's a maximum or a minimum? So right away, hopefully, we're thinking derivative, right? But what do we need the derivative of? Well, if we want to maximize the slope, the first thing we need to do is actually find what the slope is of that line, okay? So we know that the slope is change in y over change in x. So from those 2 points that we put on our graph, we can go ahead, clean everything up, and eventually we get down to our slope of being x squared over 1 plus x to the fourth. And since we'll have to find the derivative of this, I sometimes like to write it with just that negative exponent. Instead of using the quotient rule, I prefer to use the product rule. It's up to you. All right, so now we've got our slope, but in order to maximize the slope, I need to find our derivative. Okay, so this is where the calculus comes into play. So now we go through, we find the derivative. We're going to use the product rule. I'm using the product rule to find the derivative here. So the first thing, I take the derivative of x squared. I'm left with the rest. Then I have to take the derivative of the second part. So I bring the power down front, and I change that power. I subtract 1, and then that chain rule for inside. And when we clean everything up, at this point, what I'm going to do is I'm going to factor out this 1 plus x to the fourth to the negative 2. I'm also going to factor out a 2x. And then that means we're going to be left with 1 plus x to the fourth to the first power minus 2x to the fourth. So now I just clean it up. I'm going to move this guy downstairs, and 1 plus x to the fourth minus 2x to the fourth leaves us with 1 minus x to the fourth and then a 2x in the numerator. So now we need to figure out where a maximum occurs, right? So we need to know our critical numbers. So we go through and we know that our critical numbers is when our derivative equals 0 or when it's undefined. Well, it will never be undefined because the denominator is always going to be positive. It can never equal 0. So we're really just looking at when the numerator equals 0. So the numerator equals 0 when x is 0, 1, or negative 1. And now we can go ahead and apply that first derivative test. So we create our number line, right? And we go through, we plot our critical numbers, and we kind of divide our line up. And we talk about, well, what's the sign of our derivative? All right, so when I plug in a number that's less than negative 1, our derivative is positive. Between negative 1 and 1, it's negative. Between negative 1 and 0, it's negative. Between 0 and 1, it's positive. And after 1, it's negative. So what's happening to our slope? Well, it's increasing, then decreasing, then increasing and decreasing. And we're really looking for where did the maximum occur? Well, we're going to have a maximum at x equals negative 1 because our derivative goes from positive to negative. Okay? We'll have a minimum at x equals 0 because our derivative goes from negative to positive. And we'll have another maximum at x equals 1 because our derivative goes from positive to negative. So we can make our conclusion that by the first derivative test, Yes, we have a relative minimum at x equals 0, but that's not really relevant to our situation. We do have a relative maximum when x equals -1 and 1, and this is great because we were looking for those x values that are opposite of one another. So now to figure out what those actual points are, we just plug -1 and 1 into our original function to get those y values. And there we have it. Okay, let's look at this next example. A north-south highway intersects an east-west highway at point P. An automobile crosses P at 10 a.m., traveling east at a constant speed of 20 miles per hour. At that same instant, another automobile is 2 miles north of P, traveling south at 50 miles per hour. Find the time at which they are closest to each other and approximate the minimum distance between the automobiles. That's key right there, is what do we want to do? We want to approximate the minimum distance. So we are minimizing distance, okay? That's our goal. So that means I want to find the derivative of distance, which means I need an equation for distance, okay? So first let's get this diagram and let's make sure we understand where this diagram comes from. So we have a north-south highway meeting an east-west highway at point P. So that's where we stand. An automobile crosses P at 10 a.m., traveling east. So we're traveling east in this direction at 20 miles per hour. But we need to talk about this as a distance. So remember, distance equals rate times time, okay? Distance equals rate times time. So our rate is 20 and our time is t. It's unknown, okay? Then it says, at the same instant, another automobile is 2 miles north of P. So we're up here, 2 miles north of P. And they're traveling south. So they're traveling towards P at 50 miles per hour. Okay, so they're traveling. So at some point, they're at a distance. We want to find the time at which they are closest to each other. Okay, so what we need to do is we need to draw this line because there's going to be a car over here and one car here, and I want to know when is this the shortest distance. Okay, so we need to label our sides. Well, if we're at 2 miles, starting 2 miles away, this distance is going to be 2 minus 50 times t. Our rate is 50 times our time. That's our distance there. So now we can talk about this distance using the Pythagorean Theorem, right? So d squared equals d1 squared plus d2 squared. Okay, and so now we're just going to plug that in. Now another way we could write it is distance is equal to the square root of that. And now let's just make our substitution. So now we can talk about distance in terms of time is the square root of those substituted in. Cleaning everything up, so make sure you understand this part, we get our equation for distance right here. But now our job is to minimize the distance. So now we need that calculus. So now we need to go ahead and find the derivative. Okay? So we're going to go ahead and find the derivative of that distance. So when we go through, and I can rewrite that distance as, instead of the square root, that whole quantity to the 1/2. So we bring that power down, we're left with what's inside, and we subtract our power, and then chain rule of taking the derivative of what's inside here. And now we just clean it up. So I moved this all the way downstairs. 1/2 times this quantity is where I got my numerator from. I can pull a 4 out of everything here, and then taking the square root of 4, we're left with 2 out front, and we're left with the square root of this quantity here. Both of these are divisible by 2, so I just clean it up, and we get our derivative that's highlighted. So now we need to find our critical numbers because we need to apply that first derivative test. So I know that this, to find critical numbers, we set it equal to 0, and in that case, we're focusing on our numerator, okay? And when we set our numerator equal to 0, we get t as 1/29. Then we know that we have to determine when the derivative doesn't exist. Well, it wouldn't exist when this equals 0, or simply what's underneath that radical equaling 0. Well, this will never equal 0, so we don't even have to worry about that. We would get a negative number underneath this radical. So it's not even any issue there. So we have one critical number that we need to test. So we go through and we're ready to use our first derivative test. I'm saying, okay, well, what's the sign of our derivative to the left of 1 over 29? And it's negative, and to the right, it's positive. So that means d is decreasing and then increasing. So we do have ourselves a minimum, thankfully, at t equals 1 over 29. So by the first derivative test, we can make that conclusion. But our goal is to find the minimum distance, okay? So if we need to find the minimum distance, now we need to go over and do a little bit more work to finish up the problem. So to minimize that distance, I know it's when t equals 1 over 29. So now I just need to plug that value for t into my distance equation that we found up in that first step. And what we'll end up with when it's all cleaned up is we get this exact value, but we don't talk about distance in terms of that. So we could plug that into our calculator and get the approximate mileage here. So the minimum distance is 0.74278 miles, and it occurs after t is 2.07 minutes. If you have questions, let me know. See you in class.